Okay, so today we are starting our systems of linear equations topic. That is the overall, oops, I'm sorry, I did not change this. This should say topic 6. I apologize. I'm going to go ahead and change that. We are starting systems of linear equations, so today is just going to be an intro day where we talk about how to define a linear system and determine if an ordered pair is the solution to a linear system. And we're also going to do some writing of some linear systems, not solving today. We will do that. Tomorrow we'll do a little pre-activity, and then we'll do 6.3. We're going to jump to 6.3, and that'll be some graphing, which is everybody's favorite, I know. Then we'll start solving. So just today is defining and determining if an ordered pair is the solution. Okay, so in order to start this, we have to talk about what is a system of linear equations. Well, a system of linear equations consists of two or more linear equations in the same variables. And usually we're going to see x and y, but they might change it based on the situation. So for example, down here they use P and M, P for pencil and M for marker. Okay, so one pencil and one marker costs $1.50. Two pencils and one marker cost $2. What is the cost of one pencil? What is the cost of one marker? So we're not going to talk about how to solve that yet, but all they did was they said, I know one pencil plus one marker, so one pencil and one marker costs $1.50. Okay, and two pencils, so 2P plus one marker costs $2. And then they would say, how would you solve, what could you just solve that? Okay, so this right here, and this, if I write them together, and you don't have to write the ones as always. Okay, the ones in front of the variables, you don't have to write those. So this is a system right here. This is a system because both equations have the same variables, and it's always going to be two variables. Okay, two variables. That's important. We're not using x, y, and z. Okay, you technically could, but we're not going to. We're going to focus on two. Okay, so then a solution of a system of linear equations is an ordered pair. Okay, so an ordered pair that satisfies each equation in the system. And when they say satisfies, it means it creates a true statement. And I'll show you what that looks like in a minute. Okay, so satisfies means it creates a true statement. Okay, so up here, my solution would be the cost of the pencil, the cost of the marker. That would be the solution to this linear equation. Okay. So example number 1 says determine whether each of the following represents a system of linear equations. Yes or no. If not, state why. Okay, so it needs to have at least two equations and the same variables. Okay, so let's start with the first one, 14x minus 24. Okay, well, there's only one, first of all, and two, that's not even an equation. Okay, so we're going to say no, and we're just going to say not two equations. Simple as that. Okay. Okay, this second one, y equals 1.5x. Okay, that's an equation. Y equals 2x minus 1. That's an equation. That's good. Okay. Are they the same variables? Yes, y and x, so that is yes. That is a yes. Okay. Okay, number 2, or this one, not really number 2, but x equals 2 and y equals negative 3. Now, do we see, there's two equations for sure, okay, because I've got two equal signs, okay. Do I see, the y in this equation? No, but I could write 0y, and I could write 0x, and then I'd see both the x and the y. So this actually is a system of linear equations, and the ordered pair for that is actually really easy. Okay, if it's an x, y point, well, x is 2 and y is negative 3. That solution's really easy. Okay, that would be the solution to that linear system. I can see that really easily. Okay, let's bump over to this one. 2.5x minus 3.75y equals 5.5. Okay, that's an equation, but we need at least two. Okay, so this is a no, not two equations. Okay, let's pop over to this one. 5x minus 7y. Okay, well, that's not even an equation, so that's not going to work. Okay, so no, not an equation. Okay, what about this one? Y equals x and y equals x plus 5. Two equations, both have x and y, so this is a yes. Okay, 2x plus 3y equals 6. Well, there's one happy equation, but we need two. Okay, so this is no, this is not two equations. Okay, now, an example where you would have two equations and it wouldn't necessarily, actually, never mind, I'm not going to say that. I've decided not to say that. Never mind. I don't want to confuse you, so I'm not going to say that. So forget I said anything, okay? Okay, you need to flip. And I know you guys like to try to do all your U-tries at the end, but you really should be doing them as you go. That's what we would do in class, and so you're supposed to simulate what we do in class. Okay, so again, you're doing the same thing we did, determining whether each of these represents a system, and if not, state why. Okay? Okay, example number 2. Tell whether the ordered pair is a solution of the linear system. Okay, so in order to determine this, we have to plug this in for x and y in both equations and make sure we get a true statement. Okay, so I'm plugging in -3 for x. I'm plugging in 1 for y. So -3 went in for x. Plus 1 for y should give me -2. Well, is -3 plus 1 2? -3 plus 1 -2? Yeah, it is. So it's good for that one. Now we have to check both. We can't just check one. We have to check both. Okay. So now I'm going to do the same thing over here. I'm plugging in -3 for x, 1 for y. Okay. Okay, so then we have -3. Well, 5 times 1 is just 5. Okay, is -3 plus 5 2? Yeah, it is. Okay, so this is yes, it is. Okay. Okay, so let's do B. Okay, this is x, this is y. Plugging them in again. Okay, so 2 times 5 minus 3 times 2. I just plugged in 5 for x and 2 for y. It says it should give me 4. 2 times 5 is 10. 3 times 2 is 6. Is 10 minus 6 4? Yeah, that one's good. Okay, let's do the second one. 2 times x is 5 plus 8 times 2 says it should give me 11. Well, 2 times 5 is 10. 8 times 2 is 16. Is 10 plus 16 11? No, it's not. Not equal, so this would be no, not a solution. Okay, now if you tested the first one and you got a not true statement like we did here, you could stop, because remember it has to be for both. So if it's not for one of them, then it's not for the system. Okay, so must be true for both equations. That's really important. Okay. Okay, go ahead and do the U-try. Okay, example number 3. Wildlife biologists studied the weights of 2 alligators over a period of 12 months. The initial weight and growth rate of each alligator are shown in the table. Write a system of equations the biologists could use to compare the weights of the alligators. Okay, so we're going to have y is going to be my weight. Okay, x is going to be time. And then, like if I'm writing it in y equals mx plus b form, I need an m and a b. Well, of these two things that are up here, which one do you think is which? Okay, well, initial weight, initial, we know that word. Okay, that's like initial value. Okay, so that's going to be my b. It's my initial weight. Okay, and then the m is going to be my rate of growth. Okay, so m is rate of growth. So let's write it for alligator 1. So alligator 1, we're writing equations for the 2 alligators. Okay, alligator 1, alligator 2. Okay, they're both going to start with y equals. Okay, we know that. Okay, so then next comes my rate of growth. So for alligator 1, my rate of growth was 1.5 pounds per month. So this is going to be 1.5x. And then for alligator 2, it's 1 pound. So you could either write 1x or just x. Either one is fine. And then we need to do our initial weights. So that's because that's my B. So I'm going to have plus something. So remember, B is initial weight. So alligator 1 was 4 pounds, and alligator 2 was 6 pounds. Okay, so this is the system of equations. That right there. Where it's all filled in for M and B, that's my system of equations. Okay? Okay, last you try. Go ahead and do this one.